Hey, welcome back my game making friends to lesson 35 of the Dead Earth game development series brought to you by the Game Institute. I'm Gary Simmons, and in this lesson we are going to develop our zombie reanimation system. This is a system that will allow us to transition any of our zombies from a fully ragdolled state back into an animated entity. Let me also caution you that at the moment this system is somewhat experimental. It doesn't work great in all situations, depending on the final pose the ragdoll ends up in. So in the final game we'll probably put some checks and balances in place where if we find that the zombie's ragdoll has ended up in one of these troublesome positions, we won't utilize the system. An example might be if we have ragdolled a zombie and it has ended up such that it is halfway down a flight of steps, with its legs up in the air and its head down at the bottom of the stairs. In this particular instance, when we play the animation that sees the zombie climbing back up onto its feet, it's just not going to look right on a staircase. So what we'll probably do in the final game is we'll say we'll only reanimate zombies if they don't end up in a situation where the altitude between the head, the hips and the feet are vastly different. And I think this will cover probably the vast majority of cases. And you'll see in a moment when we examine the animations that we're going to use to recover our zombie from a ragdoll back up into a fully animated state, why situations such as this will cause us problems. Okay, so here's what it looks like. I'm being attacked by this zombie and then I'm going to shoot him in the legs when he comes at me. So there you go, I've shot him in the legs and now he should climb back up. There you see, kind of missed it, so let me shoot it again, but this time I'll shoot him in the side of the legs. He goes down, you'll see him reanimate after a couple of seconds. There he is, climbing back up onto his feet and then coming at us before I finish him off with a headshot. Oh yeah. So here's another example. This woman's walking through the woods. I shoot her in the legs. She goes down. But when she gets back up again, she can still walk. So she's going to get into an upright position. But I'm going to shoot her in the legs again. And she is not going to like that. And I'm going to damage her legs totally. So that if I can actually hit her legs, that is. When she goes down this time, when she gets back up, she can only crawl. So the animation that plays is her getting up from a ragdoll into a crawling motion. Here's another example. Here's the butcher. We're going to shoot the butcher in the legs. He's going to get up. He's going to come at us again. I'm going to shoot him again. Now he's going to be really pissed off. He's going to get up again. I'm going to shoot him again. Now he's going to be really pissed off. He also walks with a limp now because I've damaged his lower legs. Now when I shoot him, he's going to be really pissed off. But there's nothing he can do about it because look, I'm going to shoot him again. And now I've totally damaged his legs. So all he can do is crawl after me. Look, what a loser. Okay then, so now we know how this is supposed to work. Enough of the fun and frolics. Let's start coding this festival of pain. Don't get me wrong, it's not going to be that bad, but there are a few things that will cause us problems that we're going to have to overcome. So I think we should start by looking at some of the animations that we're going to need to get Jill from a ragdoll state into an animated state. Now we're going to need a few variants here because the animation that we play is going to very much depend on the orientation of the ragdoll. For example, if our Jill here has ended up such that she's ragdolled face down with her nose in the dirt, we're going to need to play an animation that sees a zombie recovering from a face down position up onto its feet. But obviously if the ragdoll has ended up such that it's looking up at the sky, if it's laid on its back, then we're going to need to play a different animation. And finally, if the zombie is ragdolled but it's had its legs damaged to such an extent that it can no longer walk, then what I do in Dead Earth is I say if it's led face down, then it will recover into a crawl position. So we're going to need that animation as well. But if a zombie ends up on its back, with its legs totally damaged, it doesn't try to get up and crawl after you. It essentially gets sort of stuck on its back, a bit like if you place a tortoise on its back and it can't get back up right again. But its upper body will still be working. So assuming you haven't totally damaged the upper body, you'll see the zombie led on its back, reaching out, trying to grab you. And I made this decision for the most part because I just couldn't find a recovery animation that would have a zombie that was led on its back, flipping itself over onto its front so that it was ready to start crawling. And it looks pretty cool anyway, and we can use this to have, for example, a zombie that looks like it's trapped under a car so it can't move but its arms are still flailing around trying to reach you. And you'll often see sequences like this used in episodes of The Walking Dead and other zombie series and movies. These zombies aren't very dangerous, but they make the world seem more alive and they give the player a little bit of cannon fodder while he or she is on her journey. Okay, so let's take a look at the animations we've got at our disposal to create this system. So I'm going to call it the project pane, and I'm going to drill down into the Dead Earth folder, the animations folder, the Game Institute folder, and then into the cinematic subfolder. And you'll notice that I have two animations here, one called Reanimate from Back, one called Reanimate from Front. And these are the animations we're going to use for the two main set pieces where a ragdoll has to get back up onto its feet again. So if we determine that our ragdoll is lying primarily on its back, we're going to use this animation. Okay, and if it's on its front, we're going to use this animation as the basis for the system. And next up we have this animation here called Dead to Start Crawling, and this is the animation we're going to use if we wish to reanimate our ragdoll into a crawling zombie. So as you can see, it's a pretty short animation, just shows the zombie go from kind of a dead position to a position where the hands are ready to start the crawling animation. Next up we have the trapped on back and trapped on front animation. So these are going to play whenever we determine that the ragdoll we're about to reanimate is for a zombie that has absolutely no use of its legs whatsoever. So in the case where we've smashed its legs to bits, past the point where it would even be able to crawl, if the ragdoll has ended up on its back, it's just going to lie there doing this, flailing arms in the air trying to reach you. And then in the case where the ragdoll has landed primarily facing downwards, if its legs are completely damaged, it's just going to do this. And this is what I was telling you about earlier. This would look pretty cool if you placed a zombie using this animation under like a parked car. You just see the top half of the body coming out but not being able to struggle free. Finally, we have two more animations here which are called zombie twitching on back and zombie twitching on front. This is what they look like. And here's zombie twitching on front. And these are going to be used when the zombie isn't dead, okay, so it's still got some health, but its lower body and its upper body have been completely 100% damaged, which means the zombie's got no use of its legs or its arms. So in the case where the ragdoll has ended up face down, this one will play when it reanimates, and it's just going to lie there twitching. So you'll know that it's alive, and you can go up in the game and then shoot it in the head to finish it off and put it out its misery. And here is the twitch on back. Like, once again, if the zombie falls onto its back, but it's got 100% upper body and lower body damage, it's just going to lie there twitching but not being able to get control of its limbs. And once again, you could just go up, be merciful, shoot it in the head to completely kill it and put it out its misery. So what I'm going to do now is I'm going to select Jaws AI entity, I'm going to call up the animator window, and I'm going to select the cinematic layer because that's where all of these things are going to live. And I'm going to drag these animations over first of all. So we have the Dead to Start Crawling animation. We have the Reanimate from Back animation. We have the Reanimate from Front animation. We also have the Trapped on Back, Trapped on Front, Twitching on Front. I'm going to have to give these decent names. And Twitching, although it says Titching on Back. So let's just rename these properly by selecting the state. I'll double click on them first of all, just so I can see what it is. So this is, I'm going to call this one No Body Front, all right, meaning it's got no use of its body. And I'm going to call the second one No Body Back. Obviously the Dead to Start Crawling is aptly named, so we don't need to rename that. And what's this Take 110? Okay, so this is No Legs Front, okay, so I'm going to single click on the state and call this No Legs Front. And then the second one is obviously where the zombie has no use of its leg, but is led on the back, so we'll call that No Legs Back. Okay, so let me arrange these in a better way so that we can start to create all the transitions properly. Now, all of these animations are going to be triggered from the Any State. Remember, this is what we use if, irrespective of what's happening on the layer underneath, we wish this cinematic layer to kick in from any state and go straight to the animation that we choose. So we'll put Reanimate Front and Reanimate Back there. We'll put No Legs Front and No Legs Back there, and we'll put No Body at all, front and back there, like so. And we'll put Dead to Start Crawling at an angle. And what we'll do now is we'll create some transitions from any state to all of those, so that they're set up when we wish to drill down on the specifics in a moment. And it'll also allow us to see, just in case there was any doubt, that all of these are going to be triggered from any state on the cinematic layer. So what we're going to use to trigger one of these animations, well, you're going to see later on that when we reanimate our zombie, we're going to use one of two triggers that we're going to set up now in our animators parameter list. So I'm going to click the plus sign twice. I'm going to create two triggers, okay? And I'll call this one reanimate from back, and I'll call this other one reanimate from front. So you probably know what we're going to do now, right? So in our reanimation code, when it's time to reanimate the zombie, what we will do is we will re-enable the animator, and we will set either the reanimate from front or reanimate from back trigger that will trigger one of these states. And of course, the trigger that we set will very much depend on the orientation of the ragdoll, whether it's facing down or whether it's facing up. So in the most simple case, if reanimate from front was triggered, this animation would be played here, and if reanimate from back was triggered, this animation would be played here. But of course we also have variants of that, such as if the zombie has no legs that it can use, or if it has no body, or if it's a crawling zombie. So all of these transitions really are just going to be when one of these two triggers are set, plus the conditions that determine whether the damage to the body is appropriate to that animation being played. But another thing we're going to need to do is make sure that none of these transitions have any blend time, okay? When we trigger one of these animations, we want them to start playing instantly. So if some other animation was playing on the base layer, we wouldn't want like a half-second blend between those two animations. And you'll see why that is in a minute. So what I'll do first of all is I will just open up all of these, and I will set the duration of each one to 0. Okay, so no blending. When this transition happens, it's going to go instantly from whatever the animator was currently doing on any previous layer into this state. And I'll point out why this is so important in a minute. Now also, in order to know which one of these states we should transition to when we're reanimating, we're also going to need to set up some conditions that will examine what the upper and lower body damage is. Now we know we're keeping track of the upper and lower body damage in our AI zombie state machine, but we don't currently have parameters for these, so there's no way for us to send that data into the animator so that decisions can be based on it. So let's create two more parameters now of type int. And I'll call the first one lower body damage, and I'll call the second one upper body damage. And then later on we will update that function that we wrote last lesson called update animator damage, which currently just sets whether the crawling boolean should be on or off. We'll update that so that the lower body and the upper body damage of our zombie is also sent into these parameters, so that we can then use those in our transition conditionals. Next up, we need to create the appropriate transitions back into the empty state, so that once our zombie has been animated back up onto its feet, whatever layer is playing underneath gets blended back into. So we will create a transition from reanimate front back into empty state, from reanimate from back into empty state, and the one that gets us back up into a crawling state. And those are the only 3 transitions back into the empty state we need. So what about these 4 over here? Well, these are essentially dead ends, okay? Because once your zombie ends up in this state, it can't go anywhere. It can't do anything anymore. In the case of the no body front, it's just going to sit there doing that for the rest of its life until it's killed. And the same when we use these animations over on the left hand side where we have no use of our legs. So when we transition into those, we don't have to worry ever transitioning back out. These are a one-way trip for our animator. Okay, so next up I'm going to want to add some root motion configurators to these states. So I'm going to choose add behavior, root motion configurator, add behavior, root motion configurator. I think most of these don't have any root motion in them anyway. I think the only 2 that do actually are the reanimate from front and reanimate from back. I'm not using any masks on this layer, so this layer will completely commandeer anything that's being done on layers underneath it. So we will set the root position and the root rotation to 1 on each of these. Like I said, there might be many of these animations, especially the ones where they're led on the ground, which typically don't have root motion, but I don't think it's harmful to say we want to use it. It should probably just generate a root velocity and a root rotation of 0, which is exactly what we want anyway, I guess. Okay, so what we need to do now before our animator is fully configured is we need to set up these transitions with all of their proper conditions. So for this first transition, to use the reanimate from front animation clip, which remember is the one that sees us getting back up onto our feet, there's 2 conditions that have to be met. The first is that the reanimate from front trigger has been triggered, and the second is that we have use of our legs. So if we're not crawling, because even if we've got so much damage to our legs that we've exceeded 100% damage and we can no longer crawl, the crawling boolean will still be set. Remember, the crawling boolean is always set as soon as we step past the crawl threshold with respect to the damage we've received to our legs. So we'll select that transition and we'll click the plus sign twice, And the first condition will simply be that reanimate from front trigger has been set. And the only real condition here is that crawling is false. So in other words then, this animation will be chosen if the zombie has been ragdolled face down and it hasn't had sufficient damage to the legs such that it can only crawl. So for the next transition, it's going to be kind of the same, but this time of course it will be a different trigger that will have been set. It will be reanimate from back, and once again assuming that crawling is false. The next one needs a few more conditions. Remember, this is the animation that we're going to play if we're going to ragdoll into a crawling zombie. So if I select that transition, we can imagine that the first condition is going to be that the reanimate from front trigger has been set and that crawling equals true. But we can't just leave it at that. The crawling boolean only tells us that we've sustained damage to our legs that surpasses the crawl threshold. But if we have more than 100% damage to our legs and our body, then one of these animations over here is going to be selected instead, because the zombie is unable to propel itself now using any means. So we need to do those checks here as well. So I will create two more conditions, and the first one will be that lower body damage is less than 100, and also that our upper body damage is also less than 100, because of course we need some use of both our arms and our legs to crawl. And of course, in the case where we don't have use of our arms or our legs, one of these no body front or no body back animations will be transitioned to instead. And in the case where we have lower body damage, that's 100 or more, but we still have some upper body damage use, we will trigger one of these animations over here that will see the zombie still trying to reach out with its arms, but not being able to do anything with its legs. So the next transition is this one here, the one where we literally cannot do anything. We're just a twitching zombie on the back. So the first condition here will be that reanimate from back trigger has been set, and there'll be two other conditions as well, and it will simply be that lower body damage and upper body damage are both greater than 99. In other words, we have got full damage to our lower and upper body and we are unable to move, so we're just going to be stuck on our back now, wriggling like that. And of course the next transition will be the same, except it will be when the reanimate from front trigger is set. So let's create those three conditions here. The first one being that reanimate from front has been selected, and that lower and upper body damage are both greater than 99. In other words, 100% in both regions. And the final two are when we can no longer crawl because we've got no use of our legs, but we do have some upper body mobility, so we can still flail our arms around in agony. So for that, the first one, which is the one where we are led on our back, the transitions will simply be when the reanimate from back trigger is set, when upper body damage is less than 100, so we do have some use of our upper body, but our lower body damage is greater than 99. So this is what we're going to go to. If the ragdoll is led on its back, we try to reanimate it, but it's got 100% damage to the legs, but still has some use of its upper body. And finally we have this one where it has no legs and it's reanimating from the front, so we will create once again three more conditions. The first one being that reanimate from front trigger has been set, the second one being that lower body damage is greater than 99, and of course the third one is that we do still have some use of our upper body, so upper body is less than 100. All of these transitions, by the way, should not have has exit time ticked, right? Very important. Do not tick has exit time. Now I also said that I don't have an animation to cater for the fact when the zombie has landed on its back and it does have use of its arms and legs, but it's in a crawling state. We said that we have no way of flipping the zombie from its back over onto its front. So what we did is we said if we shoot a zombie onto its back and it wants to reanimate into a crawling state, well then it can't. What will happen instead is it will just become a no legs back zombie like this. So I'm going to create another transition from any state to no legs back. I'm going to select that transition, and the other time we can transition into this state is simply going to be when reanimate from back has been selected and we are in a crawling state. Which means of course we won't ever crawl again, we will just be spending the rest of our life like that. But of course, if you did manage to find an animation that allowed a zombie to get from its back and roll over onto its front convincingly and start crawling again, well then you could set up another transition over here underneath dead to start crawling that was exactly the same as this transition here, but instead had reanimate from back instead of reanimate from front trigger being used. So if I select that transition one last time, you can see, and I think this is right, but we'll see when we test it out later, that the two transitions into this are simply that we're reanimating from back, and we were originally a crawling zombie. We can't crawl anymore, so we're just going to be stuck on our back. Or that we're reanimating from back and we just have no use of our legs whatsoever, but we do have use of our upper body. Finally, the transitions back into the empty state from these three states here should have has exit time ticked, which is actually the default. So you can see they've all been ticked, so nothing needs to be done to them. Okay then, so before we start diving into the code, we need to understand how this system is going to work and how the physics system and the animator are going to play nicely together. This is also going to allow us to see some of the problems that we're going to face and the solutions to those problems. Okay, so what I'm going to do is I'm going to press play for just a moment, and I'm going to go and shoot Zombie Jill so that she's in a ragdolled state. And then I'm going to pause the game in that state because that will make it easier for us to explain how this recovery is going to work. So I'm going to pause the game there, and then I'm going to select Omni Zombie Jill in the hierarchy so we can see the state of her bones once she's ragdolled. And we can also see where her parent container game object is, where we see the collider and the cylinder of the nav agent in the system. So when we ragdoll Jill, we know that we turn off the animator. From that point on, the animator is no longer in control of the positions and the rotations of Jill's bones. Furthermore, we also know that we make all of her body parts non-kinematic, which means they become controlled by the physics system. Unity's physics system is now free to move those bones wherever it damn well pleases. So in order to get her back out of a ragdoll into an animated state, we clearly need to make all of her rigid bodies kinematic again so that the physics system is no longer controlling them. And we also need to re-enable her animator. The problem is, if we just turn on the animator, all of Jill's bones are going to immediately snap to the positions described by the first frame in the recovery animation. Obviously, that's not what we want. What we want is, over some period of time, which we will call the ragdoll to mechanim blend time, we want the bone positions and rotations to slowly blend into the animation that is playing in the animator, so that we get no sharp movements. Therefore, in order to do that, what we're going to need to do, just before we initiate the recovery, is we're going to have to traverse all of Jill's transform hierarchy from the hips downwards, and we're going to need to take a snapshot of the position and the rotation of those bones while they're in the ragdolled state. Because remember, when we turn on the animator is going to move all of those bones so that they now represent what is being described by the first frame of the animation. So in order to blend from the ragdoll into that first frame of the animation, we need to remember the positions and the rotations of the bones in the ragdolled state. Once we've made a snapshot of all of Jill's bones so we know exactly what position they were in prior to re-enabling the animator, we are now ready to perform the blending from those positions into the positions of the bones described by the current frame in the animator. Problem is, once we enable the animator is going to automatically update all of our bone positions for us. So we need a way to get in the middle of that and override what the animator is doing whilst this blending is happening. Fortunately, Mono Behavior has a function implemented called late update. It works very much like the update function. It's called every frame, but it's called much later on in the process. The great thing for us is that late update is called after the animator has updated all of the bone positions based on the keyframes in the animation. The late update function provides us with an excellent opportunity to essentially override any of the updates that the animator has done to the transforms of Jill. In the late update function, all of Jill's transforms will have been updated such that they represent the pose described by the current animation playing in the animator. But the scene hasn't been rendered yet. Furthermore, we also have all of our snapshots of what those bones were when they were in the ragdoll. Therefore, in the late update function, while we're in the process of blending from the ragdoll into a fully animated state, we can use both of those sets of transforms, the snapshots that we took when she was in a ragdoll, and the transforms that's been set by the animator. And then we can create our own loop between those based on time, and then set those as the current transforms of Jill, overriding anything that the animator may have done. And I think in Dead Earth I use a blend time of about 2 seconds. That's the time that's taken to blend from the ragdolled state into a state where that recovery animation is now fully in control of Jill's hierarchy. Now that might all sound quite complicated, but in practice it's not. What we're going to do in the zombie startup function is we're simply going to iterate Jill's bone hierarchy, and we're going to store a reference to each of her bones so we have easy access to all of her bone transforms. When the zombie is ragdolled and we're just about to initiate the recovery into an animated state, we'll traverse that list of bones again and we'll just store their current positions and local rotations, so that we now have a snapshot of all of Jill's bones in the ragdolled position. Then we'll re-enable the animator. The animator will try and move Jill into her animated state, but in our late update function, while we're still within the threshold of the blend time, we will be the ones that will set Jill's hierarchy by performing alert between those ragdoll bone positions and the positions that the animator is trying to move our bones to. Unfortunately, however, that alone is not enough to make the system work. There's a whole load of other problems that we're going to have to address. One of the main problems that we have to overcome is when Jill is in an animated state, we know that those animations are all relative to Jill's parent hierarchy. We know that if we wish to move Jill to a position in the world, we simply move her parent game object, or in this case, her AI entity game object. This is the game object with the animator on it. And those animations will continue to play out dutifully, keeping their relationship to the parent object. However, when we ragdoll Jill and the physics system takes control of Jill's bones, those bones can move anywhere. They could tumble down a flight of stairs, they could fall off a cliff, and completely alter the spatial relationship between the bones and the parent object. For example, let's assume that Jill was at the top of a flight of stairs and then we ragdolled her. What I'm going to do is I'm going to move her parent game object up in the air like so. So imagine now she's at the top of a flight of stairs, then we ragdoll her and her body falls down the flight of stairs onto the ground. Of course here it's just dropped vertically. If it was a real flight of stairs, we may find that her bones could end up in a mess right over here at the bottom of the flight of stairs. So now not only do the bones have no meaningful relationship with the parent game object, but the zombie may have rotated around and be facing in a completely different direction to the local axis of the game object as well. So in this particular case, we can see that Jill's forward vector, according to her parent game object, her AI entity, is facing to the left here in this image. But if we look at how she's fallen down, actually, her head is now facing into the scene away from the camera. If we were to simply enable the animator now, then when the first frame of that recovery animation played, it would move all of Jill's bones up into the air at the base of the parent game object. So in the case of where Jill has fallen down a flight of stairs, when we started to recover her, what we would see is the recovery animation play at the top of the stairs. And of course the animator is doing exactly what it should be doing, because that's where Jill's game object is. It's just that the physics system has moved her bones into a completely different location in the world. So what we need to do before we start playing the animation is we essentially need to move the parent game object to where the ragdoll ended up, to try and as best as possible re-establish that same spatial relationship. And the best way to do this is to use the hip bone of the hierarchy, as that's the root of the hierarchy. So what we'll do is just before we start playing the animation, we will ask the animator where it thinks the hip bone is, which is going to be up here in the air in our example at the foot of the nav agent cylinder. And then we're going to create a vector from that hip position to the actual hip position of our ragdoll. So we've got a vector from here down to here in this example, and that gives us a vector to move our game object along such that we've now positioned it at the correct altitude and the correct position in the world, in a way moving it to the position of the ragdoll and re-establishing the spatial relationship between the bones and the parent game object. Now of course that takes care of setting the position of the game object, but the rotations may also be misaligned as well. For example, we can see if we look at the parent game object, its forward vector is facing to the left, but if we look at how Jill ended up on the ground, her feet are towards the camera, her head is away from the camera, so her forward vector wouldn't be to the left, it would be going into the scene. So what we'll do to get around this is we'll create a vector from a position that's in between Zombie Jill's feet in the ragdoll pose to her head position in the ragdoll pose. So this now gives us essentially the direction in which she is lying, in which she is facing. And then we can use that vector and our game object's forward vector to create a quaternion that will rotate our parent game object around. So in this particular case, we're going to rotate our game object around about 90 degrees so that this blue arrow, its forward vector, is now facing into the scene, matching the direction from the ragdoll's mean feet position to her head. And of course, the reason we're doing all of this is we're just trying to make sure that when we start playing that animation, in this case I've selected the reanimate from back animation. If you look at the inspector, we're just trying to make sure that we align as much as possible the first frame of that animation with the position and orientation of how Jill ended up in the ragdoll. Now once we've accomplished all these tasks, all that's left to do is determine which animation we're going to play. Is it going to be a reanimate from back or a reanimate from front? And that's going to very much depend on obviously how the ragdoll ended up. We need to find out in which direction the hip bone is facing. Is it facing up in the air, in which case she's led on her back, or is it facing down towards the ground, in which case she ended up on her stomach? Now one way that we could do this is simply take the forward vector of her hip bone in the ragdoll state and measure it against, let's say, the world up vector. And if the angle is small, then we know that she's on her back. If the angle is large, then we know that she's facing on her stomach. However, things are not that simple, because I found, as I downloaded lots of different character assets, now let me just drill down a moment here on Jill's hierarchy to show you what I mean. If I select the hip bone, you can see that in Jill, the local forward vector of a hip bone is indeed facing forward, as you would expect. So if Jill ends up on her stomach, then her forward vector is going to be facing down the world's y-axis. If she ends up on her back, then that vector is going to be pointing up in the sky. Easy, right? Now, although this was the case for most of the characters that I imported, some of the characters that I imported did not have the local space of their hip bone oriented in this same way. Some of the models had the local forward vector of the hip bone facing in the exact opposite direction, pointing out the back of the character. And some of the character assets I downloaded had the local z-axis of the hip bone pointing to the left or to the right, and in some cases even up in the sky towards the head. So there's not really any reliable way for me to auto-calculate what is facing down or facing up in relation to a hip bone. So what I'm going to do instead is I'm going to create an enumeration that is going to be exposed in the inspector that will just allow us, when we're building our zombie prefabs, to just take a quick look at the hip bone, see which way it's facing, and then set that enumeration in the inspector for the zombie so that we can tell the zombie, hey, your hip bone is facing forward, your hip bone is facing left, your hip bone is facing right, whatever, which we can then use to figure out whether we end up on our stomach or whether we end up on our back. Obviously it's a bit manual and it's kind of a bit hacky, but I think it's probably the best and quickest thing to do. But like I said, in most cases when I downloaded character assets, I did find that the local forward vector of the hip bone was facing towards the front of the character. But we need the ability to tell our code that that may not be the case, so it can compute the direction of the hip bone slightly different. And of course, once we know whether we're facing forward or we're facing backward, well then we can just contact our animator and we can set either the reanimate from front or the reanimate from back triggers, and that will of course invoke the correct animation. Now in the case where we have no body damage whatsoever, that's going to invoke the reanimate from front or the reanimate from back generic recovery animations. But we also saw when we created these transitions that if we do have upper body or lower body damage, then one of these other animations may be triggered instead. Okay, so I think that pretty much sums up how we're going to do it in theory. Now it's time to start doing this in code. So put your hard hats on, folks. This is going to get a little bumpy. So I think what I'm going to do is I'm going to start by creating that enumeration that I'm going to call AI bone alignment. And we're going to use this to identify to our script the alignment of the forward vector of our zombie's hip bone. Now just to remind you, if I select Jill's hip bone, we can see that the blue arrow here is the forward vector of the hip bone, and this is indeed aligned with the forward vector of the character in general. So we might say in this particular case, the hip bone as z-axis alignment. If it was pointing in the exact opposite direction, out the back of her, we might say this was z-axis inverted. If the blue arrow was pointing to the right, then we might say that it was aligned with the x-axis of the character, or if it was pointing to the left, the inverted x-axis of the character. So we're just going to really create an enumeration that has 6 members: x-axis, y-axis, z-axis, x-axis inverted, y-axis inverted, z-axis inverted. And I'm going to call this enumeration AI bone alignment. Now, although all of the reanimation stuff is going to be in our AI zombie state machine, Machine class, I'm actually going to define this enumeration in the base class, in the AI State Machine class, just because I think that it's a pretty generic enumeration type, and you never know, we may need to use it further down the road to describe the alignment of other bones or other things. So I'm going to open up first of all my AI State Machine class. I'm going to drill down into my scripts folder, my AI folder, and I'm going to double click on AI State Machine to open it up in Mono Develop. And right at the top where I define all of my other public enums, I'm going to create another public enum. I'm going to call it AI Bone Alignment. Actually, I'm going to call it Bone Alignment Type, and it's going to have an X-axis member, a Y-axis member, a Z-axis member, and X-axis inverted, Y-axis inverted, and Z-axis inverted. So we can use the members of this type to describe to our script the 6 different ways that the forward vector of the hip bone might be aligned with respect to the rest of the character. And like I said, I think probably when I've downloaded characters before and I have found that some of them don't have the forward vectors of the hips aligned with the forward vectors of the character in general, this to me seems like it's almost an error in the way that the skeleton's been put together. Now I can't say that for a fact because I know nothing about modeling and creating skeletons, but it just doesn't seem very intuitive to me. It seems that the forward vector of the hip should always be facing forward. So in those particular cases, it may just be that I've downloaded characters that haven't either imported correctly or were just constructed incorrectly. Either way though, if we have this flexibility, it means that if we come across any of these problems, we can cater for it. Now what our reanimation system is also going to need access to is the root bone of the hierarchy. Now you may remember that we already have this assigned via an inspector variable. I'm looking at the AI State Machine class here, and you can see that we have this transform called root bone, and if I go back to the editor, you can see if I select Jill's AI entity, you can see that we've already assigned it the hips. We did that in a previous lesson. Now we're not going to be doing anything else in the base class. All of this reanimation stuff is going to be in the Zombie State Machine class. However, you can see there's a bit of an oversight here. When I added the root bone in an earlier lesson, I made it private instead of protected, and we definitely want that to be protected as well, or otherwise we're not going to be able to access the root bone from the Zombie State Machine. And we definitely want to do that because one of the things that our Zombie State Machine is going to do in its startup procedure is it's going to start at that root bone and it's going to get all of the transforms underneath it. It's going to get all of the bones of the hierarchy so that we can take snapshots of them when we're ragdolled and we're just about to animate. So that should solve that problem by making that protected so that we can now access it in the derived class. And what we also need to do now is add another serialized protected member of AI Bone Alignment type. Remember, we've created the enumeration, but we haven't created a variable of this type, and we need to do that so that we can not only tell our state machine what the root bone is, but tell it what its alignment is. So we'll create a serialized field. Once again, has to be protected. It's going to be of type AI Bone Alignment type, and we'll call this root bone alignment. And by default, I'm going to set it to what I think is by far the most common, which is where the forward vector of the hip bone is aligned generally with the forward vector of the character itself. So this is AI Bone Alignment type Z-axis, like so. And if I save that off now, go back to the editor and select Zombie Jill's AI entity, we should now see that enumeration shows up under the root bone. But no, I have an error. What error do I have? Well, there you go. That's what happens if you spell serialized field wrong. Okay, let's give that a go. There you go. Okay, so if I select her AI entity now, call up the inspector, you can see now that under where we made that root bone assignment, we now have the options to set the root bone alignment. So if, for example, the hip bone had a forward vector that was pointing out the back of Jill, we would select Z-axis inverted. Or if it was pointing to the right, we would choose X-axis. But because it's pointing towards the front of Jill, which is by far the most common, and I think correct, we set this to root bone alignment Z-axis. And like I said, I've put this root bone alignment member also in the base class because it just seems to me that down the line you might derive different types of state machines from the base state machine class, and the alignment of the root bone might be something that you need to know about. Okay, so what we need to do now is open up the AI Zombie State Machine class, because that's where all the code that we're going to write to implement this reanimation system is going to belong. So we're going to be spending the rest of the lesson in this script. So I'm going to open up AI Zombie State Machine, and here we are once again in Mono Develop. So the first thing I'm going to add to the top of this script in this lesson is going to be a new public class called Body Part Snapshot. Now, you will recall me saying that when we have our zombie in a ragdoll, just before we reanimate it, we need to take a snapshot of the positions and the rotations of all of the bones, and that's what this class is going to represent. So the first member of this class is going to be a public member of type transform, and we'll just call that transform, set it to null. Now this is where we're going to store a reference to the actual transform that this body part snapshot represents. So in our start function, we're going to fetch all of the transforms from our hierarchy, every bone if you like that is under the hips, and we're going to allocate a new body part snapshot for each one, and then in that body part snapshot we're going to store a reference to the transform that it represents, and then we're going to store all of those body part snapshots in a list. And of course the nice thing about that is later on when we wish to reanimate the zombie, we can just iterate through that list of body part snapshots and get all of the transforms to our bones instantly without having to do any hierarchy traversal. Now simply storing a transform in the body part snapshot is not enough by itself. Yes, it gives us easy access to the transform, but in our late update function, once we start reanimating our zombie again, the position and the rotation of this transform is going to be getting overwritten by the animator. So also in the body part snapshot, we're going to need a place where we can store the position and the rotation of each bone as it was just prior to starting reanimation. So I'm going to create a public vector 3 called position, a public quaternion called rotation, and I'm also going to create another quaternion called local rotation. Okay, so we're going to use this structure as follows. In our start function, we're going to create a body part snapshot object for every transform in our hierarchy, and we're going to store in that snapshot a reference to its transform. Now, when our zombie is ragdolled, just prior to reanimating the zombie, we're going to iterate through all of our body part snapshots, and we're going to get the position, the rotation, and the local rotation of the transform, and we're going to store it in these three members so that we have remembered exactly what the bone looked like at this particular point in time. Then we're going to turn on the animator. We're going to make all of our rigid bodies kinematic again so that the animator will take over control of our bones. From this point on, the transform referenced here will be having its position and its rotation updated by the animator. But in our late update function, we have not only the transform, which will contain the newly animator updated position and rotation of the bone, but we will also have the position and the rotation that that bone was when it was in the ragdoll position just prior to animating. So we have two positions, if you like, and two rotations that we can loop between. Now the only reason why I store a rotation and a local rotation is that the rotation and the position are actually only going to be used to store a position and a rotation for the hip bone, because that's the only bone that we really need to move around and rotate in world space to align it with the hip bone in the animator. With respect to all of the bones under the animator, well, we're just going to be looping between the local rotations, and this will make a little bit more sense as we go on. So let me put a comment in there so it describes what this class is going to be used for. So now what we need to do is we need to create a list that will store body part snapshots. So we'll make sure that we say using system.collections.generic, like so. And then if I scroll down to, I have this comment here that I added in the last lesson called ragdoll stuff. Doesn't contain a lot at the moment, only the bone control type, but we will add something now. We're going to add a new private list that will store body part snapshots, and we'll just call this, well, we'll call this body part snapshots with an underscore, like so. New list body part snapshot. And then what we'll do is we will scroll down to the start function, and just after where we call the base class implementation of the start function, we will get all of the bones that are under the hip bone. So we will just make sure that we've got a valid root bone first of all. So we will say root bone doesn't equal null. Then we will create a local variable of type transform array. I'll just call this transforms. And then we will say root bone dot get components in children. Components, not component, we want all of the components, and we're looking for all of the transforms that are either on this game object or underneath it, like so. And then what we will do is we will loop through each of the transforms in that array. So we will say for each transform, we'll call it trans in transforms, like so. And we will allocate a new body part snapshot, like so. We will then set the transform of that snapshot to the current transform being processed, so trans. And now we have the transform reference stored in that newly allocated snapshot. We will add that snapshot to our body part snapshots list. So we will say body part snapshots dot add snapshot, like so. And now we know that later on, when it's time to reanimate our zombie, we can just iterate through this list, get access to all of the transforms of our bones, and we can fetch their positions and their rotations, and we can store them in the snapshot, so that when we then re-enable the animator in the late update function, we're going to have access to the position and the rotation of each bone as it was in the ragdoll pose just prior to being animated again. So let me put a comment in there saying create body part snapshot array. No, list. And I'm going to save that off. Go back, just check I haven't got any errors. And I haven't. So let's once again go up to our variable declarations, because we're going to need to add a few more variables in order to realize this reanimation system. And of course, one of the most basic things we're going to need is we're going to need to tell the system how long we wish the blend from the ragdolled state into the fully animator controlled state to be. I'm going to call this variable reanimation blend time, and I'm going to put it up here in this block of variables because I want it to be a serialized field. I'm going to set it to 0.5, half a second by default, but of course because it's serialized we'll be able to change that in the inspector to suit the animation that we're using. So as you can see, it's a serialized field of type float, and I've called it reanimation blend time, and I've set it to half a second by default. So what this basically means is in our late update function, once we've re-enabled the animator, we're going to be checking the time to see how far into this reanimation blend time we are, and that's going to be used to control the strength of the lerp for each bone from its ragdolled snapshot position into the position being described by the current frame in the animator. Now of course, in order to do that, we also need to know where we're going to start counting time from. We wish to start counting time from the very last frame that we have our zombie as a pure ragdoll. So what we'll do down here underneath our ragdoll stuff comment is we will create another private float, and we'll call this ragdoll end time, okay? And I'll set this to float.min value by default, so it's some crazy negative value. So what's going to happen then is once we re-enable the animator, we're going to check what the current time is, and we're going to store that in the ragdoll end time. And then in our late update function, we're going to keep checking what the current time is, subtract our ragdoll end time, and that will tell us how much time has passed since our zombie was a ragdoll, and then we can compare it against our reanimation blend time to see what the t value should be for the lerp between the various bone position and rotations. I also said earlier on that one of the things that we're going to need to do when we reanimate our zombie is we're going to need to try and figure out the orientation of the zombie in the ragdoll pose so that we can then move the parent game object to the position of the hips and rotate it around its y-axis so that it shares roughly the same alignment as the ragdoll. And we basically said we were going to do that by recording the position of the feet, or a position in between the 2 feet, the hip position and the head position. That will allow us to create a vector and understand the orientation of our ragdoll so that we can match it with the actual parent game object. So I'm going to need to create 3 private vector 3s to store these positions. I'll call the first one ragdoll hip position. I'll call the second vector 3 ragdoll feet position. And the final vector 3, ragdoll, oops, don't want a capital D there, do I? Ragdoll head position. And the reason we need to create these class variables rather than just storing them in some local variable in our reanimation function is our reanimation procedure is actually going to be spread over a couple of functions. So we're going to instigate the reanimation from a coroutine. But then of course it's going to be the late update function that's actually going to be performing that blend. So we're going to be calculating these 3 vectors in the reanimation coroutine, but it's actually the late update function each frame that's going to be using them to orient the parent game object so that it matches the orientation of our ragdoll, at least with respect to y-axis rotation. Now, one of the things I just touched upon, which I haven't said before, is that our reanimation initiation routine is actually going to be a coroutine. And we want to make sure that we never call the coroutine if it's already running, or if it's already running, we stop it and then start it again. We only ever want one instance of the coroutine running. So the best way to do that is to create a private variable of type IEnumerator, which you will no doubt know if you've done coroutines before is the return type of a coroutine. And then when we launch the coroutine, this variable will store a reference to that coroutine, and then we can check if it's not null, we know the coroutine's running and we can stop it using that IEnumerator. And if it's null, then we know that we can start that coroutine. And you'll see this all being used in a minute. But basically, when we call start coroutine, The start coroutine function returns an IEnumerator type, which we can store in this variable. And then if we ever want to launch that coroutine again, we can just check this variable, which I will call reanimation coroutine. And like I said, if it's null, then we know the coroutine isn't running and we can run it. If it's non-null, then we know that we need to stop the coroutine before we start a new one. Okay, the next variable I'm going to add is going to be a private float, and I'm going to call this mechanim transition time. And I'm going to set this to about 0.1 by default, a tenth of a second. Now, let me explain why we need this hacky little variable to make our system work. Okay then, so in Unity we have several different update periods. We have the fixed update, which is called by the physics system. The fixed update for this project is set to 50 frames per second, and you can set this in the physics manager. What this basically means is 50 times a second, collision and trigger messages will be processed and the fixed update function will be called. We also have the update period, which is linked to the frame rate. In other words, the speed at which the game is running on the current system. In the update period, the monobehaviors update and late update functions are called. So if our game was running at 80 frames per second, for example, the update and late update functions would get called 80 times a second, quite independent from the fixed update, which is called at 50 times per second. We also have the animator and the animations running in that animator, which very often were running at 30 frames per second. So the problem we've got is that within a given update or a given fixed update, we're going to decide that we wish to reanimate the zombie. We're going to turn on the animator and we're going to make all of its rigid bodies kinematic again so that the animator has total control over our zombie's limbs. We also said that when we're within the blending time, in our late update function, we're going to calculate the bone positions ourselves by blending from the last position the bones were in the ragdoll state to the bone positions that are being described to us by the current frame of the animator. Now, of course, we want the bone positions being described to us by the animator to be the bone positions of our recovery animation. But of course, when we first turn on the animator and we set that trigger to force an immediate transition into one of our recovery animations, that transition isn't actually immediate. It might not be processed for another 30th of a second, for example, by the animator. So what we need to do is put a hacky little delay in here that basically says that for, let's say, a tenth of a second, when we're reanimating, in the late update function, don't try and perform a loop between the ragdoll bones to the animator bones, because at the moment the animator still hasn't transitioned to one of our recovery animations. It may still be in a walk cycle or something like that. So we definitely don't want to see our bones start to blend to a walk cycle. So that's what this mechanim transition time is. We're just going to use it to bias the t value that we use for looping between the bone positions, so that once we enable the animator for a tenth of a second, which should be more than enough time for mechanim to actually update the animator and transition into the state that we want it to be in, we're not going to do anything in that time. We're just going to leave the bones in their ragdolled position. Then once this time period is over, we should be pretty safely now in the animator playing one of our recovery animations, and then we will start blending between the ragdoll bone positions and the recovery animation bone positions. Finally, we're going to add another serializable float, which I'm going to call reanimation wait time. Okay, and this is the length of time that the zombie is going to stay in a ragdoll state before it begins to reanimate again. I'm going to set this to 3 seconds, I think. And the reason I use something long like 3 seconds is because, let's say our zombie has fallen off a wall or fallen down a flight of stairs. From the time we ragdoll it, 3 seconds should be pretty much long enough for the ragdoll to come to a stop. And this reanimation system really only looks any good if the reanimation happens once the ragdoll has stopped moving or falling. So once we initiate our ragdoll coroutine, that first thing that coroutine is going to do is it's just going to wait for 3 seconds before it actually reanimates the zombie. But of course, this is a serializable float, so it's going to show up in the inspector and you can tweak this. And we may find that the reanimation blend time is a little bit short as well. We may want to have a bit of a longer blend time there. In fact, let's put it to something like 1.5 seconds. Remember, this is the time at which we're blending from the ragdoll into the recovery animation. So I think that'll be okay. Okay, so now what I'm going to do is I'm going to scroll all the way down to where we implemented that take damage function, which, remember, is the function which is going to call our reanimate coroutine. But at the moment, when you look at our take damage function, we just have a series of comments in there that says to do reanimate zombie. So that's where we're going to call our coroutine. And also there's another one down the bottom if I remember correctly. Yeah, down here, to do reanimate zombie. Remember, this was the function we wrote in the last lesson, where it just checks whether we should be ragdolled or not based on what part of the body was hit, and it adds the damage to the upper and lower body damage and things like that. So if you missed the last lesson, make sure you go and watch it, because it's this function which is very crucial to when the reanimation actually happens. So what I'm going to do underneath this function is I'm going to create our coroutine, which is going to be a private function which of course returns an I enumerator, and I'm going to call it reanimate, like so. And it takes no parameters. And what we'll do now is we will put the code into our take damage function, which actually calls this coroutine and also stores the returned I enumerator, so that we can check if the reanimate coroutine is running or not. And we'll have to do this in two places in this function, but we'll work on this one first. So the first thing we'll do is we'll get a reference to our coroutine. So we will say reanimation coroutine equals reanimate, like so, and then we can say start coroutine, and then we can pass in our I enumerator, which of course is our reanimation coroutine variable, like so. So of course now we have a reference to this function. We can always just check before we start it that it's definitely stopped. So we can say, assuming we have a reference to our reanimate coroutine, we will call mono behaviors stop coroutine function, passing in that I enumerator. So we're just making sure that more than one copy of this coroutine never executes. And then what we'll do is we'll copy that, and then we'll paste it back up at the top of the function, or more towards the top of the function. Where was it? Here, where we had the other to do. There you go. And the only difference between those two invocations of the coroutine is this code block, you will recall, happens if we shoot something that's already in a ragdoll. So assuming we haven't killed it, if it was in a ragdolled state, then we just make sure it stays ragdolled, and we start the coroutine again. So if the coroutine was running, but it hadn't started reanimating it yet, it was still in that 3-second wait period, we would just cancel it and call it again, starting that 3-second wait again. But down here is when it's in an animated state, and we shoot it into a ragdolled state. And once again, we just do the same thing. So let's now go down and write our reanimate function. I think what I'll do is I'll put some comments in here. I'm going to pause the video and just comment this a little bit. Oh, actually guys, I've made an error there. I should be checking that it's not null there, because this isn't a boolean, it's an I enumerator. So if reanimation coroutine doesn't equal null, then stop the coroutine. I need to do the same up here as well. If reanimation coroutine doesn't equal null. Okay. That should stop me getting any errors. Let me just go and check that is the case. Okay, well I am getting an error saying that not all code paths return true, but that's going to be the case because we haven't written our coroutine yet. So at the moment it's not returning anything, but don't worry about that. Actually guys, looking at the time, I'm going to snap this lesson off right here, because we have quite a lot of code to write in the reanimate coroutine and also in the late update function. So I think I'm going to save that to the next lesson. Now, I hate having to leave you hanging here with half-finished code, but I do need to keep the videos to a sensible length so that I can actually deploy them to our LMS. So we'll pick this up in the next video. Thanks for listening, guys. See you next time.